Hello and welcome back. In this module, we're going to look at the longer term hydration. Previously, we've looked at the induction period up to about 3 hours. Then we've looked at the main hydration peak, and we've seen that this is controlled by nucleation and growth of CSH. Now we're going to look in the longer term. And this period's really not been studied as anywhere near in as much detail as has this induction period and the main hydration peak. Perhaps because it's rather difficult to study, because in terms of what you can measure, for example, the heat evolution is shown here, there's not much going on. Or at least it seems so. But that's very deceptive, because at this point here of about 1 day, the degree of hydration would typically be about 50%, and the amount of strength would be maybe 20-25% of the final strength. So there's an awful lot going on in this later period here beyond the first day. And in this module, we're going to try and look at what some of these things might be, although I have to tell you now that we still don't really know that much. If instead of looking at curves in the differential form, as we saw previously, if now we look at the integral curve, the cumulative heat curve, we can plot, for example, the variation of the water-cement ratio, and we can plot different mixtures with different substitutes of quartz, and we can kind of identify 3 different regimes. We can identify this regime here, which we've already looked at. We've called this previous periods 1 and 2, and we can see that even though the details of this main hydration peak might vary a lot, as we saw in the previous 2 modules, it's fairly similar. And then over here, in the long term, we also see a very similar behavior for all the systems. And we'll come to that at the end of this module, but at the minute we're calling this period the densification period, for reasons I'll explain. And then in the middle here, we see that this is where we get the biggest variation for all these different systems. And what we've really done in these different systems is vary the amount of space available for the hydrates to deposit in. And this is why we call this middle regime, which I've called 3A here, we call this the space-controlled regime. So basically what this means is that hydrates are continuing to form until they've used up all the easily available space. And this occurs around about 6 days for a water-cement ratio of 0.4. Now we can get other very interesting insights on this regime if we use this technique called proton nuclear magnetic resonance. So what we do with proton nuclear magnetic resonance is we depend on the behavior of protons, which are basically hydrogen atoms. And by applying a magnetic field, we can align the little spins of these nuclei. And then we can remove the magnetic field. The spins relax. They go back to the kind of random orientation they were in the first place. And by looking at the timing of this relaxation, we can make various deductions about the pore sizes. And the real strength of this technique is that we don't have to dry the sample. So most techniques that have been used classically to look at microstructure, you have to dry the sample before you look at it. In this case, it's exactly the opposite. In fact, the pores need to have water in them to get the signal. And what we can do many different measurements in situ from the same sample. And here we see a sort of little schematic of a pore structure. And you see there's big pores and smaller pores. And the essential aspect is that we have water molecules in these pores moving around. And if they hit the surface, then they relax very, very quickly. So this means if we have water, like you may have in a bottle of water, this will have a relaxation time of about 4 seconds. As we move to smaller pores, then because the water will have a very high probability of hitting the surface before too long, we'll go to shorter relaxation times. small pause to shorter relaxation times still, and the shortest relaxation times are for bound water, which is found in the crystalline hydrates. And this is explained in a lot more detail in these references that are given here. These are results from the work of Arno Müller, and we can see how these spectra evolve over time. And what we can identify in these spectra is different populations. So we start with the shortest one with the shortest relaxation time, and by analogy with this diagram here, the shortest relaxation time is expected to come with water that's firmly bound in crystals. And this we can show to be the case by quantifying the signal here. We can see that it corresponds to the water which is in portlandite and in yttringite. And I should perhaps have said at the beginning here that what's important in this series of experiments in these spectra is, in fact, we can quantitatively measure all the water in the cement paste. So this is the bound water. This has the shortest relaxation time. And as you see here, it matches really very, very well with water in the calcium hydroxide and the yttringite. So logically, the next shortest relaxation time has to be coming from the interlayer water in the CSH. So this is the interlayer water in the CSH, and from analyzing the signal, we can see that this is coming from dimensions of around 1 nanometer, which is roughly what we'd expect to be the area for water in the interlayer of the CSH. So this next clear population we can see here, which starts a little bit bigger and then comes down to this defined size, is in fact what we call the gel water. So when we looked at CSH, we talked about the gel porosity, and in those gel pores is the gel water, and we see this has a quite well-defined characteristic size of about 3 to 4 nanometers. And finally, the rest of the water over here is now capillary waters. So going back to the beginning, we can see at the beginning we start with just capillary water, then we start to form CSH, and then finally the gel pores. And at the end, in these experiments, which are done with sealed paste, we have very little capillary water. So we can look in more detail at how those populations evolve over time in terms of their amount and also in terms of their size. So if we look at the capillary water, what we see is over the first day, of course it's corresponding to this main heat evolution peak we've been talking about, the amount of capillary water decreases very sharply, and also its size decreases. So it starts off with a characteristic size of around 73 microns, and here already after 1 day it's gone down to about 10 nanometers. And then after this point here, at about 2 days, we see that the amount decreases, but the size no longer decreases. The size really stays constant at a size of about 8 nanometers. And because of this consistency of size, we then decided we give a new name to this area. We call these interhydrate pores. Now, why did we call it interhydrate pores? Because if you look in the TEM and you see these needles of CSH like we've talked about in the previous modules, you can see between these needles we have spaces of about 8 nanometers. And we really feel now that this is making up most of the capillary pore space of a well-cured mature cement paste, is these very complex spaces between these CSH needles. We can see a similar picture by using a very different technique, which is mercury intrusion porosimetry. And many of you have probably heard a lot of negative things about mercury intrusion porosimetry, but when we've compared mercury intrusion porosimetry to proton NMR, we actually have now a lot of evidence that mercury intrusion porosimetry is giving us a very good picture of what's happening in the pore space, as long as you dry your samples correctly. And I really need to stress this point, because if you dry your samples by putting them in an oven, you form a lot of cracks. You get any or kind of thing by MIP. If you do it by this technique we use, which is called solvent exchange, where you dry your samples in isopropyl, then you can get really nice reproducible results. And what you see is that this breakthrough diameter here, when the mercury really starts to penetrate into the sample, this is going down quite rapidly during the first few days, but by the time we're at about 3 days or 14 days, then after that point it doesn't go down anymore. So it goes down to a certain critical pore entry size, and then it doesn't go down more, even though the overall amount of the capillary porosity is continuing to decrease. So we think this fixed critical pore entry size here is the same as the interhydrate space we saw here. Now, if we look at what's happening in the hydrates, we can now look at the interlayer water. So the interlayer water is between these sheets of CSH, as shown in red here. And unsurprisingly, during the main hydration peak, this is going up quite fast, and then subsequently it's going up, but more slowly. We add the gel water, as we see here, and at the beginning, in the main hydration peak, the gel water is going up in parallel, in the same ratio as the amount of interlayer water, but from this point at 2.2 days, in this case of this white cement, we see that the gel water is really plateauing. And at very long ages, it maybe even goes down a little bit. So the amount of gel pores is not a constant amount in all the CSH. The amount of gel porosity varies. We form a lot at the beginning, and then really no more after a certain time. Very probably this is related to formation of outer CSH, those needles we've been talking about quite a lot, and then afterwards when we get the inner CSH, we really see that this doesn't contain any gel porosity. And from all these measurements, we can get now quite a lot of more detail about what's happening in our CSH. We can look, for example, at the density, and we can look either at the density of this kind of solid part. These are these nanocrystalline regions we talked about quite a few lectures ago. And we can look at the amount that's forming in the bulk, as we see with the gel porosity here. And the solid has quite a constant density over time of about just below 2.7, 2.8, whereas the bulk, the average density is increasing because the proportion of gel pores is decreasing. So at the beginning, we have quite a low density, below 1.8, and by the time we're getting to a high degree of hydration, we're seeing that this is going to a density of about 2.1, which is very much in line with the kind of densities that have been estimated from other techniques. We can look also at the amount of water contained in the CSH. So again, for the solid nanocrystalline regions, the amount of water content is around 2 for each solid chain unit, whereas for the bulk, the amount of water on average is decreasing because we have less water proportionally in the gel pores. So from all this, we can really make an update of the repetition of the solid volume over time. So this was done already about 60 years ago by Powers, and he measured the proportions at long times and then said, well, okay, I'm just going to draw straight lines as a function of the degree of hydration. And we find very good agreement between our repetition of the volumes at long ages here with what Powers found, except that now we can differentiate the solid that he just measured as one single hydrate into CSH here and calcium hydroxide and ettringite here. The main difference we see is the amount of gel water is not a linear function of the degree of hydration, but it increases very rapidly at the beginning and then stays constant thereafter. So let's go back to our cumulative heat curves, to these different stages. We've looked in this middle zone, zone 3A here, and we've seen that this is controlled by the amount of space available. But what's happening in this very long term? Well, again, we can analyze the slope of these curves, and we really don't see any indication that it fits with the kind of kinetics we would expect from diffusion. What we could hypothesize at this stage, and I stress this is very, very tentative as an idea for a mechanism, is that what perhaps we have initially CSH like this, where we have our nanocrystalline regions and the gel pores, and then in very long ages those gel pores are getting filled in by extra layers of CSH. So the amount of extra hydration between here and here is really very, very small, but it's contributing to this densification and to some gain in mechanical properties. So I stress this is still quite a tentative idea here, and needs to be worked on more in the long term. So to summarize what we've seen in this lecture, we've looked at some ideas of what's happening in the long term. And what really seems to be important, certainly in the first few days, is the amount of space available for the hydrates to form, which are determining the rate of reaction. And after about few days, say about 6 days at a typical water-cement ratio of 0.4, we only have pores below quite a small size which are left. And this small size does not allow the growth of hydrates in the classic way that we've talked about previously. And this kind of slowing down of the reaction then means we transit to a regime in which we have really more densification of the CSH. And that's really highlighted by the studies we've done on proton NMR, which also indicate that we need to refine the Powers model because the development of the capillary and gel porosity are not linear functions of the degree of reaction. So after this few days, we get this very slow reaction, which the mechanisms are still unclear, still a subject of ongoing work. So now we've really seen the mechanisms. We've been concentrating most of all on the silicate phases, and what remains now is to look at the reactions of the illuminate phases, how this fit in. This will be in the next module. And then finally, we'll bring this all together to look at how the microstructure can be visualized in the scanning electron microscope, for example. So thank you and see you next time.